Good afternoon, everyone. My name is Dr. Chaudhary. I'm an associate professor with the Department of Electrical and Electronic Engineering of the Independent University of Bangladesh, and also the director of my research lab, the IoT Photonic Simulation Laboratory. Today, I want to speak to everyone about the latest research that's been going on in my lab, which is primarily pretty much computational research. It deals with the use of plasmonic nanoparticles to enhance the optoelectronic performance of solar cells. So, I would like to say, sorry. Okay. Because we watch main topics like summary. So, I'm only data that but I will run through them fairly quickly to give you an overview so I can hit the highlight points. The details of it for I'll be more than happy to speak to you after the end of the session. So the problem area is currently solar cells have very limited efficiency. The crystalline solar cell market share mainly silicon based, approximately 25% efficiency. I think solar cell on a call. So আমরা যখন বলি solar cell efficiency মানে solar cell এর কাজটা হলো যে light absorb করবে, electricity create করবে. So they absorb photons of light and they create electrons. So এখানে যদি আমি বলি 15% efficiency, what I'm saying is that for every 100 photons it's absorbing, it's only creating 15 electron hole pairs. So 85% of the absorbed photons are being wasted. So clearly, there's a large room for improvement. Specifically, যদি আমরা চাই the solar cell দিয়ে আমরা fossil fuelকে large scale replace করবো. To manifest that and help that happen, we cannot stick to only 25% or 50% efficiency. We have to go more. So there's many kinds of research that's going on all across the world, how to engineer more efficient solar cells. Our lab, one of the labs, or other labs around the world also do it, is to use patterned metallic nanostructures on top of the solar cells to increase its efficiency. Just a cartoon দেখালাম যে এখানে কি বুঝাচ্ছি মনে করেন এটা লাল যদি সোলার সেল হয় তার উপরে যদি আমি বিভিন্ন রকমের metallic nanoparticles দিয়ে কোট করি, then there's a possibility that we can increase the light absorption and also after the light is absorbed increase the light absorbed to electron generation ratio. And these nanostructures can be in different forms. It can be just completely homogeneous particles, or you can have core shell particles or even multi-particle systems. So a researcher fundamental like a property it's called surface plasmon resonance. So the first thing we need to know is what is surface plasmon resonance. Quickly, basically metallic nanoparticle at the electron cloud, right? And the electron cloud has a fundamental frequency of oscillation. এখন ওই oscillating frequency তে যদি আমি light hit করি যার frequency match করে তাহলে একটা resonance condition create করা হয়, তখন ওই ইলেকট্রন গুলো আরো বেশি অ্যাম্পলিটিউডে oscillate করবে. That's the resonance condition. In that condition, that nanoparticle will absorb or scatter light much more efficiently in that frequency range. So এটা হলো যে surface plasmon resonance. So for example, এখানে যে metallic electron cloud আছে, if I hit it with a light, the wavelength of a frequency take a match for it, you create a resonance condition. And resonance condition করলে you will create বিভিন্ন রকমের wavelength of frequency তে light absorb করবে অথবা reflect করবে. And so what are the factors that govern this? So for example, key metal I'm used for this, gold, aluminum, copper, silver, that determines কোন frequency the resonance হবে. Second, metallic nanoparticle size technique. Third, metallic nanoparticle shape technique. Fourth, আমি যদি একটা সারফেসের উপরে ন্যানোপার্টিকেল ডিপোজিট করি, একটা ন্যানোপার্টিকেল থেকে আরেকটা ন্যানোপার্টিকেল কত দূরে, interparticle distance আমরা pitch করি. And there are other factors too which govern কোন ফ্রিকোয়েন্সিতে আমরা এই absorption অথবা scattering দেখব. যেটা বললাম আগে আমার ল্যাবে we do our computational work. We use a licensed commercially available software from ANSYS numerical called FPDP solutions. যেটা আমরা optical part solution করি, and then the electrical part solution করি with another software called charge or device, also from the same company. So the whole part is optical simulation of light interaction with metallic nanoparticles. And the electrical simulation is once the light is absorbed, how do you create or how much of the electrons are you creating? So these are some of the quick detailed job on some of the simulation setups for our optical and electrical simulations. We can talk about the details later if you have questions. So the last 2 years, I want to give you an overview of what we have done in the last 2 years. So the number one things we did is, I mean, homogeneous particle here is stuck, or can I design some other particles, for example, core shell particles? And I can molecular metal use for the silver and aluminum were mentioned repeatedly. These are very reactive metals. So if I cover with another material, I can create chemical isolation. And plus, other optical property will change. That's right here, core shell nanoparticles. Then I mean, the silicon is the major absorbing semiconductor material for solar cells. Economic plasmonic enhancement, but is that translatable to other materials that's used in solar cells? For example, cadmium telluride, gallium arsenide, and also tangible with perovskite solar cells. And this conference is called 4IR for Emerging Future. So it kind of into key type of solar cell, key type of nanoparticle design for what are the properties? Simulation I can do infinite number of possible permutations. On a time like on an effort like this, is there an intelligent way of actually narrowing down your subset? You can use many kind of artificial intelligence-based algorithms like genetic algorithm, which would help optimize the different particle useful. And last from nanoparticles fabricate definitely there will be fabrication defects. When you draw something in, or when you simulate something, you can simulate perfect conditions. But reality is never perfect. So a defective array to the finite. Our plasmonic solar cell performance increase simulation check. So the first project was to design aluminum silica core shell nanoparticles. So it kind of core aluminum and shell silica, and we tried different kinds of thickness, diameters of the aluminum and thicknesses of the silica. As you can see, as you can vary the core shell diameter and ratio, the optical properties of the aluminum changes. As you can see, this is the wavelength, this is the cross section. So that can more or less, it's highly dependent on core diameter and shell thickness, and more importantly, a gray window technology, the optical window, you can silicon absorb for it. So what I'm at nanoparticle design for long resonance frequency there, you can silicon absorb for this. So I have to make sure that my resonance properties of my nanoparticles overlaps that of the optical window of the substrate I'm trying to use. There has to be a marriage of the two. So this is what shows us that this works. So we tried 3 different configurations, putting the particle on top. I told you here how much silicon substrate. The particle can embed the body. And the third will be the sandwich configuration. You can detail this is all idealism, computational approach. So fabrication is very difficult to understand, but proof of concept is done. So top configuration for different particle nanometer diameters and shell thicknesses, we can see enhanced short circuit current density and also optical absorption, and embedded it to compound. And then when you have the sandwich configuration, you get, for this configuration, you get a very high amount of light absorbed as well as current generated. And the efficiency, the short circuit current density and efficiency change is quite significant. We have 13.4 change in, so 100% change in efficiency. Bare silicon, nanoparticle 9, 100% or 100% or 170 in this case, sandwich configuration. Now this work was presented in the 6th International Conference Development in Renewable Energy Technology. It got to 2nd position in the Best Paper Awards, and these are my students who worked on this project. Now, quickly I want to say that, as I said, I'm into simulation for this. There is hundreds of different kinds of nanoparticle silicon design. So how to best organize this? The genetic algorithm is one AI-based technique. Focus করতে পারি. I can try to optimize my design using some genetic algorithm-based techniques. And this is some of the properties of genetic algorithm. A custom with the collaborating with Professor Shamin Kaisar of the Institute of Information Technology of Jamnagar University. So উনার সাথে কাজ করে দেখার পরে দেখলাম যে on the top configuration বিভিন্ন রকমের কোর ডায়ামিটার শেল সাইজের জন্য আমাদের শর্ট সার্কিট কারেন্ট ডেনসিটি জেনারেটেড যেটা আমরা এফটিডিটি তে সিমুলেশন করছি তার সাথে জেনেটিক অ্যালগরিদম প্রেডিকশনের মোটামুটি ভালোই মিল আছে same thing for embedded systems. Again, this is something to do with their error ratio. The error ratio is also comparable. And so the conclusion here is that using core cell nanoparticles on top of the solar cells actually works. The second thing is that you don't have to have only a homogeneous material. Second is that in order to optimize this system, you can use artificial intelligence-based techniques to help us, give us a good range of what to work with. And this can, of course, open doors for lots more interesting collaborative work between artificial intelligence techniques and solar cell design. The second project is dealing with, I mean, even fabricate nanoparticles solar cell, there'll be all kinds of defects like this. She is a better expert than I am. Nanoparticle deposition or creation করার জন্য you will have particle size disparity, particle shape disparity, particle interparticle distance disparity. আরেকটা দেখবেন এখানে you can deposit nanoparticles in different configurations. And it doesn't have to be square array, it doesn't have to be random, it can be hexagonal. এটার ভিতরে অনেক ডিফেক্ট দেখা যায়। তো এইগুলো বানানোর সময় যখন আমরা ডিফেক্টিভ পার্টিকেল দেখবো, how does আমাদের plasmonic nanoparticle performance কিভাবে ড্রপ করবে অথবা ভালো হবে। So we simulated some defects in our simulation. মনে করেন এখানে পার্টিকেল শেপ চেঞ্জ হলো, এখানে মনে করেন পার্টিকেল একটা মিসিং অথবা পার্টিকেলটা sorry this is এখানে দেখবেন যে পার্টিকেল মিসিং, এখানে দুটো পার্টিকেল মিসিং, এখানে random particle distribution. So we simulated different kinds of defective conditions that will potentially occur. So আমরা ডিফেক্ট একটা মডেল করতে চেষ্টা করেছি। So বিভিন্ন ডিফেক্ট আমরা দেখি যে more or less regardless of the defect you're using, compared to a bare silicon substrate, you're still getting quite large, about 20 to 30% increase in efficiency, given all the different defects. Contamination particles happen, pitch difference, missing particles, size problem. So that was very encouraging. And the last thing I wanted to talk about was one of the latest research that we're doing is everything we're talking about translatable to other substrates, or is it just focused on only silicon? We worked on cadmium telluride. I'm interested in silicon solar cells. The first question is, why cadmium telluride? Number one, the main reason is cadmium telluride is a far more better absorber of light than silicon is. So তাহলে এটা লাভ কি আমার? লাভটা হলো যে আমি যদি একটা মেটেরিয়াল ইউজ করি সোলার সেলের উপর যেটা অনেক ভালো বেটার অ্যাবজর্বার অফ লাইট, তাহলে আমরা সোলার সেলের থিকনেস অনেক কম হবে। কোথায় অ্যাপ্লিকেশন করতে পারবো? সেলফোন দিয়ে চালাতে পারি। সেলফোন হ্যাজ এ বিগ প্রবলেম, ব্যাটারি। আমি যদি সোলার সেল দিয়ে ব্যাটারি ইউজ করতে পারি সেলফোন, তাহলে আমি এত বড় সেলস সোলার প্যানেল করতে পারবো না সেলফোনের ভিতরে। I need an ultra thin layer of silicon for solar cells. Another one would be calculator, হাতের ঘড়ি, Fitbits. All these mobile devices, if you can in some future get rid of battery and actually make them run through solar cells, potentially you need an ultra thin layer of these materials. So cadmium telluride is a candidate. And again, when we have a silver nanoparticles, coat column, a cadmium telluride solar cell, lo and behold, we get an absorption increase in the optical light absorbed. The short circuit current density is also giving us about a 25% increase in current, and also about a 25% maximum increase in different particles and particle sizes. So, for example, this is 150 nanometer diameter silver, 150 nanometer diameter aluminum nanoparticle. So, these are nanoparticle. For these two particles, silver and aluminum, we're getting an increase in efficiency. And this is a video which shows that I can light to the ashe, ekhane nanoparticle ache and niche hobe solar cell. Eta loop video, eta abar loop ashbe. So you can see the light coming, interacting with the solar cell. A lot of this light is concentrated around the nanoparticle, and then it goes inside the solar cell. So this is the enhancement effect right here, as you can see here. So this is for silver and this is for aluminum. So there's a neutral, খুবই neutral কাজ মাত্র 6 মাস কাজ করার আছে result সবই the work is still need to do. It's incomplete work. It's work in progress. Our student location and sort of কাজ করছে এটা নিয়ে. But what I would like to conclude my talk by giving some major conclusions. The eight conclusions are key. Number one, using plasmonic nanoparticles, you can get increase in the optoelectronic performance of solar cells. Number one. Number two, this plasmonic enhancement phenomenon is not limited to only silicon, which is granted market share silicon and gashi, but can also be translatable to other materials such as gallium arsenide, cadmium telluride, and henceforth. And the third one is if you're thinking of building or fabricating these plasmonic solar cells, you do not need to have a perfect array of these nanoparticles. Effective array also gives you significant enhancement. So if you're useful to technically useful, I can use potentially cheaper fabrication methods like sputtering to create these nanoparticles on top of the solar cell and still get pretty good enhancement. So it's like saying I'm either brand new gari kini 50 lakh taka diye tarpore ami the recondition gari kini 10 lakh taka diye motamoti comparable performance definitely I'll go for the recondition car. I don't need to have a perfect array. I can have quite a lot of defects and still get pretty good enhancement. It's good for countries like Bangladesh. The fabrication equipment here are high-end equipment here are on challenges. So sputtering material number one, sputtering for $12,000 as far as I know. So that was it. So this is some of my selected references, acknowledgements. I want to acknowledge Independent University of Bangladesh for funding this research for the last 2 years. I want to thank Professor Samim Kaiser of the Jahangir University giving us the genetic algorithm. Calculations they have করেছে এটা আমার expertise না এটা ছিল. Of course, my students who are some of them who are here in this room today. Thank you very much. I would like to thank you. So, it was a nice presentation. It's coming to the simulation with planning experiment. Then I'm experimenting for years. Fine, there's no power of the prevention. As you step back, the defects are defects is always not a negative entity. But question is that the defect will deal for change defect reproducible. Again and again, same or defect sign five. I mean, the application I mean, the portion of the product established এবং fabricated. I mean, the portion the portion maximum established তার initial parameter নিয়ে আমি আমার simulation use করতাম. There could be that might give me some realistic information at the bottom line. Now, previous class I'm going to known unknown নিয়ে খেলার চেয়ে আমি যদি known যেটা সেই knownটা নিয়ে ফেলি আমার একটা স্টেপ আগে যেতে পারবো। আদারওয়াইজ একটু ডিফিকাল্ট যেটা হবে আমি তা ফিল করি ফার্স্ট প্রোডাকশন আমার কম্পিটিশন করে কারণ আমরা বাংলাদেশে আমরা চাই না যে এখানে আমাদের লোকাল কিছু কনফারেন্স ব্যাপার করলাম আমরা লোকাল কিছু ইয়েতে পারি এরকম না কিন্তু আমাদের গভর্নমেন্ট যথেষ্ট ফান্ডিং দিচ্ছে অনেক আমি জানি না আপনারা অ্যাপ্লাই করে কিনা মিনিস্টার সাইডে আমরা প্রাইভেট ইউনিভার্সিটি দেওয়ার জন্য আই মাইসেলফ এজ এ মেম্বার অফ দ্য পিয়ার রিভিউ কমিটি প্রাইভেট ইউনিভার্সিটি আমি মানে হাইলি আমরা ফাইট করি private university do not fire. Should do আমরা develop about public not things don't be like that. Public development বলতে ওই জিনিসটা মাথায় রেখে আর কি যে একসময় আপনারা সুইচ করতে যেতে পারেন এক্সপেরিমেন্টে আপনি আগে মানুষের এক্সপেরিমেন্ট ইউজ করেন আপনার সিমুলেশন আবার আপনার সিমুলেশন আপনি যখন সুইচ করতে পারেন এক্সপেরিমেন্টে that might be wonderful. That's very good suggestion. Porcelain particles যেটা ইস্যুটা আছে না এখানে দুটো নাম্বার 1 হচ্ছে অপটিক্যাল প্রপার্টিজ আর আরেকটা হচ্ছে কেমিক্যাল ইস্যু মানে বারবার যে আমরা বলতেছিলাম যে আমরা aluminum, silver. So sometimes you might have a nanoparticle that are chemically more inert, for example, gold. In the optical it's giving us poorer results. So that's the trade-off. Thank you, sir.
Yeah, sure, please. I definitely at 170% change with
efficiency. So our normal efficiency I would say about 12%. No, but 12% থেকে 100% বেশি maximum. এটা স্যান্ডউইচ স্ট্রাকচার ছিল। স্যান্ডউইচের উপরেও আছে নিচেও আছে। It's like double pincer attack. কিন্তু এটা I know fabrication is a huge challenge, but it was a proof of concept.
Thank you.